Hello everybody. I have here two very different lights with the same very common problem. This is a 9 watt Wessex branded bayonet cap light bulb, and this is a 50 watt LED Vance branded floodlight. Both of these have the same issue. They have both failed very prematurely for the same reason. They have both massively overheated. This one I removed from a customer's premises like yesterday because they reported it was no longer functioning. And as is usual practice, I asked them to send a picture of the light fitting so I knew what I was replacing. In that picture they sent, I could see, you can see them here, lots of little dots all over the front glass. These were spaced out all over the front of this in the position it was. I figured that'll be just bugs, because that's fairly common with an LED fixture like this. You get bugs inside it, they die, drop. It's not uncommon, especially here. So that's what I assumed it was. When I've taken a look at it, these are not bugs. They are all of the LEDs, which is why it doesn't work. This has got so hot that it would appear the solder has melted and all the LEDs have dropped off the board and were lying on the glass on the floodlight. This bulb here, again, same story. It was, I should have said, the customer says this was fitted 6 months ago by a different contractor. Judging by the condition of it, I think it has been fitted for longer than 6 months to give it the manufacturer their due, but I don't think this has been fitted like 10 years ago. This has been a fairly recently fitted device. I would guess maybe a year, 18 months at most, judging by the state of it. So this should not have failed in 18 months. Certainly not. This bulb here has been in use for about 5 minutes. I put it into my work light, which is basically a bulb holder on a flex. There is no light shade at all before anyone goes on, oh, you can't put that light shade, that's why it overheated. It was in an open bulb holder on a flex. It was on for about 2 minutes. It started flickering. A couple of minutes later, I was sitting there going, what's that smell? And then I looked around and, oh my god, it's smoking. This was ridiculously hot, and it's a bit hard for you to see, but all this plastic here has melted badly. This has got ridiculously hot. So again, I'm not sure it's a manufacturing defect or a design flaw, but both of these have massively overheated and thus failed extremely prematurely. So I'm interested to take these apart for you, and we will have a look and see if we can work out why these have overheated so massively. Is this a manufacturing issue? Is it just bad luck? Or is there a design flaw with one or both of these products? Especially given that I have had 2 bulbs from the same box of this fail in the same manner, which makes me suspect it's either a manufacturing issue with a batch of these or a design flaw. The other thing I should have mentioned is I'm not familiar with either of these brands. This is just a random bulb that I think my dad does most of the purchasing for us. He got it from somewhere, I'm guessing probably one of our suppliers, so a wholesaler somewhere. It won't have been the most expensive you can get, but it won't have been cheap shite either. And this floodlight here we did not fit, but I'm pretty sure LED Vant is a brand that our local wholesaler sells, so again, it shouldn't have been total crap. And I wouldn't have expected a failure mode like that from either of these products, given where they have come from. So yes, let's have a look inside them and see if we can work out what's gone wrong. One moment, please. I think just for the ease of it, I'm going to start with this because it's going to be easier to get apart than the other one, and it is smaller and simpler. These basically work. You have 3 main parts. There is the metal bayonet cap, which is where the electrical connections are made, the plastic body, and the transparent dome. Usually these domes, just twist off like that. This is not great because honestly, if you twist that off, this is all then live, so you could poke this and get quite a nasty shock. I'm not loving that, but it's how they all seem to be. If we have a look here, this is a DOB-based thing, so driver on board. You can see these chips here are obviously burnt. They've got very hot indeed. This looks to be a linear regulator-based design. We have a full bridge rectifier here. Should get a pointing thing so my finger is not confusing it. Let's focus on that. There we go. We have a full bridge rectifier. We have, I suspect, a linear rectifier. We have a little transistor MOSFET thing here. One of these will be the... this is the incoming supply. I think this is probably a smoothing capacitor. We have a inductor, some resistors, capacitor, and the chips, which, as I was saying, a few of these, I don't know if you can see, but they're blatantly burnt fairly badly. I'm going to pop this circuit board out. There won't be much underneath this, maybe a fuse, but I'll see. This will need cut out though to get the silicon off, so one moment. So, I think I know what the problem with this is. The issue is, I don't know if you can see, but there is a metal lining on the inside of this plastic moulding. That's fairly common for these. That's basically the heat from this LED array and the driver gets dumped into the aluminium substrate of the PCB. So you have a layer of copper, then a very thin layer of fiberglass, and then an aluminium substrate, which is what this is here. The aluminium substrate then transfers the heat into this metal housing here, which is supposed to then radiate it out. This is not particularly effective, particularly on higher powered bulbs. I think mostly the issue in this case is that there is just very minimal contact between the bottom of this board and the edge of this lamp here, especially given that there was silicon on the contact surface, which will have been further preventing the transfer of heat. I'm not sure why this has got so hot though, because clearly this plastic is melted, so this must have been ridiculously hot if the thermal transfer is not great. Which I'm assuming is probably, you can see, I don't know if you can see in the light, but the copper has delaminated as well and is all bubbled up here. This is, I suspect, to be honest, I'm not sure. There's something to do with this circuitry that's made it dissipate way more heat than it's supposed to have done. I'm going to have a look at the datasheet for this chip because it is marked and see if that can give me any clues about what might the problem be, but I don't think I'll be able to find out much more than the thermal transfer between the substrate here and this does not look great, and it must be a design flaw with this linear regulator. Other than that, at first glance, this design actually looks quite good, and the smoothing capacitor has been put underneath as well, which is nice because it means that it is sort of shielded somewhat from the heat and also does not affect the light output. But yes, one moment, I'm going to look at the datasheet for this chip. So a very quick Google, because I haven't done much research, has not shown anything for this chip. It is marked DBGCJA, which is a bit odd. Usually you would have some letters and numbers rather than just letters. Anyway, I can't find anything. It'll be a linear current regulator almost certainly. I'm not going to sketch the circuitry out. Here is a closer up picture of the circuit board for you to have a look at. You can see the burnt chips in that a bit clearer hopefully. Anyway, this out of the way, now on to the floodlight. So, now onto this floodlight. As I was saying, at first glance, this actually looks fairly good. If we flip this over and have a look at the sticker on the back, we can see some things that are, generally speaking, a hallmark of a good product. We have here FP... Oops, I'm having things avalanche. FLPFM 50W/4000K SYM 100S black BK. That will be the model number for this. LED vamps, I was saying, it is a 50 watt output, 4000 Kelvin being the colour temperature, 6000 lumens being its light output, a 110 to 277 volt input. 277 volt is very high. the highest voltage you're allowed in Europe is 253 volt. Beyond that, it is a problem, and I will be complaining to the network operator that their voltage is too high. But it's not uncommon. I've seen a few industrial power supplies that are rated up to 277 volts. Oh, you know what that'll be? I'm thinking about it. In America, they have 277 480 volt 3-phase. That'll be what it's for. 50, 60 hertz, 555 to 218 milliamps, and IP65, which I would buy. This is probably, I would have expected more than IP65, given how this has been in very close proximity to the sea for a long time, and it has not got water in it, especially from the Har. I don't know if this is a Scottish word or not, but a Har is basically a sea fog. It is an absolute bastard of fog, and will get into just about anything. So the fact this has not got water inside it is a big plus. The other interesting thing of note is power factor is better than 0.9, which means this has a power factor corrected power supply in it, which is again a hallmark of a very high quality product. It says operating temperature is 50 degrees Celsius, obviously, because solder usually melts about sort of 170 to 230 degrees Celsius-ish. That means this is got far beyond 50 degrees Celsius. I have never come across a solder alloy that will melt that low. It says here 2011 on it. I don't think that this has been fitted in 2011. I'm guessing that is a design date. If this has been fitted in 2011, I would expect it to be far more corroded than it actually is. But I don't think this has been fitted for 6 months either. It would be less corroded than that if it was only 6 months old. But yes, let's get this apart and have a look. I see some little slots here, which I suspect I'm going to be able to pop the front bezel and the glass off with a screwdriver, but I'm going to have a look and see, so one moment. So, as expected, this plastic bezel has just clipped off. This glass panel I would rather not break. I'm going to assume this will just pop off as well. I'm being very careful here not to shatter it, because I do not want to have to try and clean up broken glass all over my bench. Just try with a knife maybe and see if I can get any movement out of it. It is siliconed on. Let's see if we can cut. Give me a minute, I'm going to see if I can get this off without breaking it. 1 second. So much for the whole not breaking it thing. That was a bit of a mess, and also I broke the tip off my knife. I'll have to fix that later. But other than that, this does actually look quite decent. It appears that, yes, if we get this reflector out the way, the glass on this was toughened at least, so it's not sharp. I do have to be careful though not to end up with a splinter of glass in my finger, just in case there's any of them around. But we get this reflector out of the way. We have a very burnt LED matrix. You can see here how badly burnt they are. Actually, it seems I was wrong. Those things rattling about inside were not, in fact, the chips, but it was the phosphor off the top of the chips, which has come off, so you can see the chips are bare. So the solder hasn't melted, so it hasn't got quite as hot as I thought it did. We have a actually quite nice looking driver board there as well. The thing I'm curious about though is what the thermal coupling is like between this, oops, I'm dropping my screwdriver, this LED panel and the back of the light. This is usually where the issue is, that the panel is not appropriately thermally coupled to the light. I think, I might be wrong, but I think this driver still works, because when I went to remove this, there were still a couple of LEDs that were actually dimly glowing on this before I isolated it to remove it. So I think this driver is still working, it's just the chips are broken, and bingo, there is our problem. This should be covered in thermal paste, and it is not. So there is not a proper thermal connection between the back of this panel and that a metal casting on the back. To be honest, they have ruined this, because this would actually be a fairly good light, I think. I'm going to take this driver out and we'll have a look at that in a second. But I'm pretty sure this would be a fairly good light if they would have just put some thermal paste between the LED board and the aluminium casting. This would have been absolutely fine. But because they've saved like half a penny on thermal paste, they've written off this light. That kind of thing annoys me so much. But I'm going to get this board out and we'll have a look at it, so 1 second. So, I've been having a look at this, and I must say I am very impressed. This is, yeah, this is good. I like this. This driver is amazing. This is obscenely complicated because of the fact it's power factor corrected. You will notice a few things. No primary smoothing capacitor. That's one of the main things, because it has to vary the amount of power it's drawing with the shape of the sine wave in order to... actually, I should explain what power factor even is before I'm going into this. 1 second. So, what is power factor? Ignore this for the moment. This is some math I will explain in a second. Power factor is basically the amount of phase shift between the current and voltage waveforms of an AC supply. I will draw out for you what that means. So in AC you have a sine wave voltage waveform like this. If your power factor is 1, which is unity, so 1 equals unity, that means that your voltage and current are perfectly in phase, so your voltage and current would both look exactly like this, right off top of each other. That would be a resistive load, so say a incandescent light bulb or a heating element. If you have an inductive load, say a motor, or a capacitive load, say, I'm trying to think what would be a capacitive load. Most things these days are slightly capacitive, like a phone charger, that kind of thing. I think they're usually capacitive loads. But a load that is either capacitive or inductive, not purely resistive, it means that your current waveform will either lead like this or lag like this, the voltage slightly. When you have that, that basically means that we need to put more current through the wire to do the same amount of work. The way we differentiate those is watts is the work that is actually being done, volt amp is the amount of power that we appear to be transmitting. So volt amp is for volts times amps, like what you'd have on DC, volt times amp. Whereas watts is the actual power being used. So if we go over here, I'll explain what all this means. 50 watts of real power is how much this light fixture uses. If we assume it had a fairly average power factor of about 0.6, which is fairly normal for a switch mode supply, it would be drawing 83.33 volt amp of apparent power. So our generator has to produce 83.33 volt amp power. We have to transmit 362 milliamps of actual amps down the wire, where we only need 117 if we were, or sorry, 217 if we were to have a power factor corrected board like this. So we're saving 145 milliamps of basically wasted current per fixture. So that works us out, if we have 33.33 volt amp of wasted reactive power per light fixture. I should explain this. So as a individual domestic consumer, you only get billed for this, the real power consumption. You do not get billed for the apparent power usage. Commercial and industrial consumers, though, do get billed for both. They get billed for all of this, the apparent power, not the real power. So if you have, let's say, a big campus like a university or something like a shopping centre, a very big building, let's say that you have 2,500 of these light fixtures around your campus. They're on for 9 hours a night to light the place up. If we take the 33.33 volt amp of unnecessary reactive power that this would use if it had a non-power factor corrected supply, times our 2,500 lamps, that's 83,325 volt amp, or 83.325 kilovolt amp per hour. Times that by our 9 hours per night, which again in Scotland I would say is fairly conservative. In some area, sometimes of the year that might be way higher than that, because sometimes it can get dark here at like 3:30 or 4 p.m. and it can get light not until like 9 or 10, particularly if you went out to Shetland or the very north parts of the country. Yeah. So 9 hours a night is not an unreasonable amount of time if you took an average over the whole year for somewhere very far north. We times this 83,325 times 9 hours a night is 749,925 volt amp hours a night. I've rounded this to 750 kilovolt amp hours for simplicity of future maths. If we times that by the year, we are now wasting 27,347 kilovolt amp hours of energy that we do not need to be consuming. If we take a fairly average price for a commercial or industrial client of 30p per kilovolt amp hour, that works out to £225 a day, or £8,204.10 a year in unnecessary expenditure just on your lights. So imagine how that then scales across your computer power supplies. Will be the same. All the lighting inside the building will be the same. All of the chargers are the same. Like, every load that you have with a switchable power supply in it will be this bad. And you can imagine how over the course of a year that can get a massive expenditure on basically absolutely nothing. Because this 33.3 volt amp per fixture is not being used. It is just being temporarily stored and then returned to the grid, but you're still billed for it because the transformer still has to be big enough to supply it, the cable still has to carry it, there's still losses involved in that. So this can very quickly escalate to get very, very, very expensive, which is why you get power factor corrected fittings like this. So this one would only actually draw the 217 milliamps, not the 145 extra that we don't need. So that then saves us this, so it saves us all this money, £225 a day. So let's have a look at this and we can see how it is different. This is extremely complicated and I'm not going to explain all of it because, to be honest, I have no idea how most of this stuff works. I'm not an electrical engineer. Well, I'm an electrical engineer, not an electronics engineer. Different. But we have, if we go over this very simply, these here are all filtering, basically. These will be metal oxide varistors. We have some filtering inductors. There's something I can point with, rather than my fat finger. I had a screwdriver I was using somewhere here. Anyway, I'll use my pen. So we have, this is not better. We have metal oxide varistors. We have a filtering inductor, another filtering inductor, another filtering inductor, filtering capacitors, more filtering capacitors, more filtering capacitors, but interestingly you will notice no primary smoothing capacitor. If we flip it over, the other thing you will notice a conspicuous, so here is our rectification. I have no idea what these diodes are doing. Probably snubber networks, I would guess. So we have our rectification here, but you will notice the conspicuous absence of any smoothing. There is no smoothing on the primary side, and that is because the smoothing basically will cause the power factor issues. Because we are not drawing power evenly across the sine wave, we are drawing power unevenly at different points. So we have here, this is the control chip. That's the smart of it. That does all of the magic to do with varying the amount of power it's drawing with the incoming waveform. We have a switching transistor here, transformer here, a flyback smoothing capacitor for the power to this chip. This is the PIR sensor. I cut that off because I couldn't get it out in one piece. As I said, we have the switching transformer here, secondary rectification, and then these big fat capacitors on the output, which are the smoothing for the LEDs, and then another filtering inductor. This here is another interesting one. This is a little basically buck supply, which is stepping the high voltage for the LED array down to a much lower voltage, I think this is 5 volts, to run the PIR sensor, which is interesting. The other thing you will notice on this, which is not a problem, is this is not isolated. That is because it doesn't have to be isolated, but it means you have to treat the output of this as if it is mains. So you could get a potentially mains derived shock off the output of this. It is not separated. That's very common though in LED drivers, they usually aren't. But yes, this is very, very well designed. There's a lot of filtering, there is a lot of very complicated stuff that goes on, most of which inside this little chip here, in order to make all the magic happen. I'm very impressed. I like this board a lot. I'm hoping that this still works, and I can use it for something else. And it's just this LED panel which is baked by the total lack of thermal compound on the back. Actually, I might try that. Let's see if it explodes. One moment. So the usual disclaimers go, don't try this at home. I'm an electrician. I know what I'm doing. Live exposed circuit boards are not a good idea. Anyway, without further ado, I'm going to power this on, and hopefully it doesn't explode. No bang, that's good. Now, where can I put my meter so we can both see it? There we go. And I'm now going to try and get a reading 154.9 volts. Yeah, so that seems to be working fairly good actually. That's fairly reasonable voltage for something like this because the arrays are lots of series LEDs, so they need a very high voltage to work. I'm going to keep this driver. I like it. Yeah, that's good. Right. Yeah, I don't know what to say here. I thought of something I should have said. There are two kinds of LED drivers, constant current drivers and constant voltage drivers. If you take, this is a constant voltage driver, I know that because when you look at this panel, there are resistors here. So this is a constant voltage driver, not a constant current driver. If you run a constant voltage driver with no load on it, they're usually fine, they don't care. If you run a constant current drive with no load on it, you will destroy it fairly quickly. So if your LED panel does not have resistors and is just a big string of LEDs connected to a board like this, do not run it without a load on it, you'll damage it. If it has resistors on the LEDs, you'll probably be fine to run it for a while without loading it, but don't do it for too long anyway, just to be safe. Anyway, with all this out of the way, both these lamps, same issue, massive overheating. This one I'm pretty sure caused by the lack of thermal paste. Other than that, this actually seems really pretty good. I love this driver, it's This is probably one of the nicest drivers I've ever seen for an LED floodlight. Yeah, I love this thing. It's amazing. If they had just put thermal paste in this so that these LEDs didn't bake the crap out themselves, this would be probably my new favourite light. I would be fitting this everywhere. But because of this, nah, not touching it. These LED bulb, I'm not sure what happened with this. The lack of thermal contact between the PCB and the casing, I think, probably plays a part in why these fail so often. But this casing's clearly got ridiculously hot because all the plastic's melted. So, I don't know. I think this must be some sort of electrical fault with the board. In terms of what that is, I don't know. But yeah, I'm wondering if maybe it's like a broken solder joint or something, so the current sensing isn't working properly and it was massively overdriving itself. I don't know. Anyway, but yes, this thing, not great. I mean, they serve a purpose. These little bulbs, cheap, cheerful, but don't last particularly long. These linear current ones, you can actually modify. Big Clive has a video about doing that, where you can cut by removing resistors and changing the values. You can make these run at a lower current, so they'll last basically indefinitely. So that's nice. This driver, love it. This lack of thermal paste, hate it. Overall, interesting video. Hope you enjoyed it. Hope you learned something. If you've got any questions, comments, suggestions, whatever, drop them down below. I read everything, and yeah, I'll see you in the next one. Bye.